All right, students, let's get into circuits and let's look at the element diagrams. Now, one thing you should always try to do whenever you're trying to calculate or solve a circuits problem, you need to draw it, okay? It's very, very important that you draw it and label it, and no two circuits are probably ever going to look the same unless, of course, they're identical. I think that's a no-brainer. There are some basic symbols that you should come to familiarize yourself with. This is on a circuit diagram. This is what we often call a schematic. That's what your battery looks like, the wire will look like on the drawing, and a resistor should look like on a drawing, okay? And that's how you want to draw them. And typically when we draw the battery symbol, we draw it like this. We draw a long and a short side, okay? And the long side is the positive and the short is the negative, okay? That's typically the best way to draw it, okay? All right, now, okay, so those are some symbols. Here's some more symbols. What a bulb looks like, a junction would look like, a capacitor would look like, and a switch would look like. So you do need to familiarize yourself with these, and these drawings are in your textbook, okay? All right, now, not sure exactly what page those are on. Yeah, they're on page 728. Okay, Kirchhoff's laws. Now, in order to have a good understanding of how current flows through a circuit, you need to understand Kirchhoff's law. And basically, and we touched on this a little bit in the last chapter, 22, but he has two basic laws, his junction law and his loop rule. And basically what it says is that the sum of all the currents in a junction should equal zero, okay? So when you sum up all the currents in a junction, they should equal zero. Now, I'm not going to rip your eyeballs out trying to do these. My Cal-Base folks, now we really get into Kirchhoff's rules, and we have to do simultaneous equations. You can also solve it with a matrix, okay, because basically what we're looking at here is a series of linear equations, okay? But, just for the sake of this being trig-based, I'm not going to be too rough on you on Kirchhoff's rules and problems, all right? So we see here, and you can write this junction law either way. If you move this back to the other side, it becomes this equation here. So what does that mean? That means that the current going into a junction has to equal the current going out of a junction. Now here they have it coming in, and so that means the current going this way and this way both of these have to equal this side over here, okay? Well, that goes back to conservation of charge, if you remember when we talked about that, okay? All right, of course, we talk about gravitational potential energy. It's much like electrical potential energy. Of course, the only difference is that gravity is not repulsive. Okay, now, it's only attractive. So when we look at the energy then, the same applies for energy going through a loop, that when we sum up all of our potential electric energy, it should equal zero, okay? So it tells us here that the electric potential around any loop or closed path must be zero as well. And here they show you just a diagram of a battery and two resistors and what the voltage would look like as you travel around this loop and get back to the negative side of the terminal. You would see that the voltage should be zero, okay? Okay. All right, now, so we write Kirchhoff's loop law. The voltage around any loop should be equal to the sum of all the voltages, which should be equal to zero, okay? And so, again, that's just a simple rule to remember, just like his current rule. The loop law is the same thing. When you get all the way around, it is zero. Now here's some basics of how to use Kirchhoff's loop law, and you can read these. These are in your text. These are on page 729 and 730, so you can read over these. And again, now this is important to remember too. Notice here that when you're going around a loop, and see sometimes in circuits you have multiple, let me just draw you one real simple here. You may have multiple batteries, okay? Well, notice we have 3 loops, well actually 2 loops, but 3 branches. And you say, well, how do you determine a branch? A branch is wherever 2 or more wires come into a junction, okay? All right, so you've actually got 3 branches, all right? Now, okay, so looking at this diagram, notice we've got let's just say we've got 10 volts and 5 volts here. Notice we've got 2 different voltages. Well, you have to decide where you want to start going around and what direction you want to start going around. Typically, I always like to start with my highest voltages, name that loop A and this loop B, and draw which way my current is going to flow. Whichever way it flows around one, you have to flow it the same way around the other. And then you start in one particular area, like if I was going to start up here in the top left-hand corner, I go all the way around and I come back. And notice that I hit the positive, negative, but I land on the positive. Well, notice this is what it's telling you, that if you're going upstream and you cross a voltage source, an EMF source, notice that if you hit the negative but land on the positive, then your voltage is positive. If you're going the other way and you hit the positive and land on the negative, then guess what? Your voltage is negative. Very easy to remember, okay? And these are very good rules to remember. Now, same thing applies, well, it's actually the opposite applies on current. Whenever you're going through a resistor, you are dropping voltage. You see, current times resistance is voltage. So you are dropping voltage, okay? You're using energy. See, you've got to understand that the resistor is absorbing the energy, okay, in a sense of terms, okay? So you are dropping voltage. Now, what if I came through a loop and I was going the other way? Well, notice that we come out on the positive side, we are adding voltage, all right? Now, you say, well, how do I know when I'm going to add and when I'm going to drop? Well, here again, you always draw your diagram first, label your loops, and determine which way you're going to go around the loops, and you do it the same way on both of them. So going this way, let's just say we start right here and go that way, and 2, you always have to assign current direction. So I would call this I1, and I would call this one I2, and really it doesn't matter, it's arbitrary, and I would call this one over here I3, okay? And you got to realize I3 is here and here and there, and I2 is just here in the middle, and I1, this is I1 right here. See, it's going back this way, I1, okay? All right, and this right here is I1, okay? Now, so my equation then is going to be equal to I1. My current equation is equal to I2 plus I3, okay? All right, so that's my current equation. Then we have to start going around our loops. Well, if I start here and go clockwise, like I said, and come all the way around this loop, let's just say that's 3 ohms and this is 2 ohms and that's 4 ohms. All right, we come around. Notice right here, we're going to come all the way around this loop right here, and it would be what? Well, it would be minus 3 I1, and then hit the I2 branch, and we're going through it now, going with current flow, and again, that's arbitrary. 2 I2. And then we hit here, the junction, and we come back around. We hit the negative side and land on the positive. Plus 10 volts is equal to 0. Because remember, the sum of all the voltage is equal to 0. Okay? So that would be another equation. So here's one equation. Here's 2 equations. And then our third equation, all right, I'm going to start right here. I'm moving with current flow. Okay, so that would be my third equation would be what? 4I3, negative 4I3. And you say, why is it negative? Because I'm going with the current flow. I'm dropping voltage. Hey, wait a minute. I hit the positive side of my battery, but I land on the negative. That would be minus 5 volts, okay? and then I come on around and come back up this loop. Hey, wait a minute, I'm going the opposite direction, so that would be plus 2I2, okay, is equal to 0. And so now I've got 3 equations and 3 unknowns, okay. I got 3 currents, 1, 2, 3, and guess what? You can't have any more equations and unknowns. And so then I could start solving my simultaneous equations. And what would I do first? Well, notice I got an I1 and I2 here, and I got an I3 and an I2 there. And so I'll tell you what I do. You add both of these equations together, and notice how the I2s cancel each other out beautifully. And then you can solve for, you have to do a substitution. You have to get all equations the same. So I would come right here and substitute I3. I'd say, well, I3 is equal to I1 minus I2, right? Okay, and so then I'd just come right here and I'd substitute I3, and then I'd subtract out my I2s, okay? All right, after you've added them up. Well, after you added them up, actually what you're going to have is 6. You're going to have, no, you're going to wind up with a negative 2I, let's see, I1 minus I2. Yeah, you're going to wind up with a positive 4I2, so you wind up with 6I2 total. So how can I cancel that out? Well, multiply this one up here times 3, and they'll subtract each other out, okay? And then go from there, all right? So that's how you do a Kirchhoff's loop rule equation, okay, and problem, all right? All right, now series and parallel circuits. What do we mean by series and parallel? It's very easy to understand. Series, we have one path. The best thing to do to remember is that series are connected directly to each other with no junction in between them. In other words, we have a single pathway for current to flow. Okay? Single pathway for current to flow is a series, okay? That is a series circuit, all right? All right, and here are we'll define parallel here in a minute. And here and there's a parallel circuit, okay? And notice we have alternate pathways. Notice this little quick check I thought we'd do. Which is the correct circuit diagram for the circuit shown? Well, notice you've got 2 right here that's in parallel, so it'd have to be this one right here, wouldn't it? And it is, okay? All right, brightness of the bulbs. Now, again, since both of these are identical and they're in series, they will have the same brightness. However, if that bulb right there dies, guess what? That one dies with it. Why? Because the pathway for current to flow has been broken. Okay, now, if any of you have ever heard about the first Christmas lights that were made by, I can't remember who made them. I think General Electric put out some of the first Christmas lights back in the early 1900s. And if you ever find a set of these, they're worth a lot of money, okay? Especially if the bulbs still work. But what would happen is and Christmas lights, by the way, are still wired in series. You just have multiple sets of series linked together. And you say, well, now wait a minute, then how do they work if one of them goes out? Well, I'll tell you what they did. Now, in the early days, when they had the Christmas lights, a bulb went out. Guess what? The whole string went out, okay? So we had a problem. So what did they do? Someone got really smart, and they come in here, and here's your wires coming up, and then there's your coil of wire that produces a light, and then the wires going on out. Okay, well, guess what? If that burns in 2, we're in trouble. Well, I tell you what, let's fix that, and let's put what's called a shunt right here in the bottom part of the bulb connecting the 2 wires, because look, the current here and the current there will be the same, but what happens is if this burns out where the filament is, it produces light, guess what? The current will continue to flow, and that was an easy fix for Christmas lights, okay? And so once this was discovered, all Christmas lights then would burn forever, okay, as long as the bulb didn't blow. But it was much easier to change them because only one would go out, not the whole string, okay? All right, now, so let's move on. Series resistors, again, you have a single pathway for current to flow. It's very self-explanatory, okay? And then you have how we calculate the resistance. Now, going back to this particular setup, we've got 2 resistors here and here. Well, how do we solve what is called the equivalent resistance? Okay, that's called the equivalent resistance. It's really easy. We just add them all up. So anytime you have resistors in series, it's very easy to find the equivalent resistance. You just add up all the resistors, okay? So if it's 2 ohms and 3 ohms, that'd be a total of 5 ohms, but your equivalent resistance, okay? All right, now, one thing about resistors in series, you got to remember something, that the amperage will be the same across both those resistors, okay? However, the voltage will be different. The voltage divides, and it'll divide according to how much resistance you have, okay? Okay, all right, so there's your resistors, and of course here's talking about the current. The current, regardless of how many resistors you have, will be the same on every resistor, even if you got 1,000 ohm and a 1 ohm. Guess what? And they're in series. They both have the same resistance. So we have what is called the equivalent resistance. There's another equation. All we do for resistors in series. Now this is for series, okay? Series. Then you just add them up. Okay, what about parallel resistors? Well, here we see two side by side. Notice parallel, we have alternate pathways for current to flow. Okay, so we have alternate pathways. You say, what do you mean? Look, if this one right here blows, guess what? Current can still flow to this one, because it's still connected, okay? If this one blows, well, guess what? That'll keep burning too, okay? You have current can go this way and current can go that way, all right? So you got alternate pathways for current to flow, okay? Now, one thing about resistors in parallel, now, they're different, okay, from those in series. Series, the voltage divides on resistors in series. However, resistors in parallel, the voltage is the same. And so what do you mean? That means if I come in here, right here, and right here, and I check my voltage, and I check my voltage here and here, guess what? No matter what the resistance is, the voltage here and here and here and here will be equal. They'll be equal to each other, all right? Now, one thing you need to try to remember, though, that the current in a parallel resistor splits. So notice how the current and the voltage from series to parallel flip-flop, okay? Series circuits, the current is the same in all resistors, but the voltage divides according to how much resistance you have on each resistor. Parallel combinations, the voltage is the same across each resistor, but the current divides, okay? And that's what they're telling us here, all right? Now, what about finding the equivalent resistance for parallel resistors? Well, notice it is the reciprocal, okay? In other words, you take, and actually that should be 1 over Req, okay? Because what you have to do is you get your fraction and then you take the reciprocal, okay? All right, now, okay? So always remember that. You can't leave it a fraction. You have to take the reciprocal of it because we want Req, all right? So 1 over Req is equal to 1 over this, and then Req would be the reciprocal of that, all right? So add them all up. Let's say you had a 2 and a 3 and a 4, okay? Well, you're going to add them all up, okay, and then take the reciprocal of them. You got 3 fractions there. Add them up, take the reciprocal, and then that'll give you the equivalent resistance, okay? All right. Now, of course, these will have the same brightness if they are identical. But now, one thing about it is, if you have 2 in series and then keep the voltage the same and input 2 in parallel, you will have brighter bulbs if they're in parallel. Why? Because the voltage drop across both of them is the same, whereas on series it divides. Okay. All right. So here it tells you that the equivalent of several resistors in parallel is going to always be less than any of those single resistors in that particular group, okay? And that's why we use parallel combinations, because we can, if we want to affect how much current is being used across a particular circuit or part of a circuit, we use parallel combinations because we don't have near the resistance, okay? All right, remember, because why? Well, because we have alternate pathways for current to flow. Now, an amp meter, of course, is something that we use to measure current, okay? and I think that's kind of self-explanatory. An ideal ammeter is one in which we have a zero resistance. But again, that's ideal, but we know that all ammeters have a little bit of resistance in them. I mean, because they have wire in them, all right? And so, you know, wire has resistance in it. Now, notice here that when you check the current in a circuit, notice how the current, you have the positive going in, and the negative coming out. Now, what do you mean? In other words, you put your ammeter in series. What do you mean? Notice you've got a single pathway for current to flow through that ammeter. That's why you always have to hook up your ammeter in a circuit, okay? All right? Now, what about measuring voltage? Well, voltage is a little bit different. Remember, what are we measuring? We're measuring the potential difference across particular resistors or devices. We don't have to just say a resistor. A device is a resistor. It has resistance in it no matter what it is. All right, so notice how we put the voltmeter parallel. Notice that it is parallel. It is parallel. See how that lines up to the device, okay? And so whenever we test the voltage, check the voltage on resistors, no matter whether it's series or parallel, you always have to hook your voltmeter up parallel to the resistor, okay? See how that's parallel? See how you touch it here and here? It's not in series, okay? All right. Okay, complex circuits. Now, when we look at more complex circuits, basically, what are they talking about? Well, you know, when you get into combinations of, for example, here we have 2 in parallel and 1 in series, okay? And so you say, well, how would I solve that circuit? Well, you got to realize something that, and you say, well, how do you know if it's in series or parallel? Look, you got a single pathway here, but you've got alternate pathways here and here, okay? And now with the switch open, the only way current is going to flow in this particular diagram is right here. So you've got 2 in series, single pathway of current flow. But when you close that switch, then you have 2 in parallel. And so what you have to do is you have to realize that these 2 are in parallel, and then they form 1, which is in series with A, okay? And so you just have to be methodical, and when we work some problems, I'll show you what I'm talking about on these circuits, how we reduce these down, okay? All right, I'll show you how to do that. Now, let's move on, talk about capacitors in series and parallel. Of course, a capacitor we know is a device that stores charge, stores voltage, and of course we know that the potential difference across the capacitor is going to be equal to our EMF source. And you have different arrangements with capacitors just like you do with resistors. You have parallel combinations and series combinations, and there are particular ways you have to calculate what we call the equivalent capacitance. All right, here we have a parallel capacitor, and notice that the total charge on 2 capacitors is equal to what? Well, it's equal to, the total charge is equal to the sum of what? Both capacitors, isn't it? Right? So parallel capacitors, they have the same voltage but different charge, okay? So the voltage is the same across them, but the charge does what? The charge adds up, doesn't it? Each one has a different charge. All right, what about those in series, okay? All right, now, and again, there's your equivalent capacitance. How do we find the equivalent capacitance for capacitors in parallel? Now notice that we calculate it differently. Notice that the CEQ for parallel capacitors is just the sum of all the capacitors. Remember, parallel resistors, it was the reciprocal. It was the reciprocal of the resistance, okay? So keep them separated. Now, what about those in series? All right, now, so series capacitors, they have the same charge, so the same charge here is the same charge here. However, the voltage is different, okay? So the voltage is different. on a series capacitors, okay, those in series, all right? So the potential difference across both capacitors is the sum of the voltage across the two. So what does that mean? Charge is the same, but the voltage here and the voltage here is different if they're different size capacitance, okay? So here it tells us that the analysis hinted the fact that the series capacitors have the same charge, all right? Now how do we find, and of course notice they put that little -1 in there. That means you got to take the reciprocal, okay? I didn't catch that a minute ago on that other one. But you got to remember you got to take the reciprocal once you add all these up, then take the reciprocal of it, okay? I really wish they wouldn't write it that way. I wish they'd just say 1 over CEQ is equal to all of that and leave that off, but maybe it won't confuse you, okay? All right, now, okay, what about RC circuits? RC circuits are those that contain resistors and capacitors. They are very, very useful. We use them all the time. We use them in electronic components like crazy, cameras especially. Anything that has a time delay as far as charging or discharging capacity built into it. If it's you say, okay, you flip the switch and it has to charge for a little bit and then it starts operating, or you flip the switch and it discharges and then it starts to operate. This is through the use of what is called an RC circuit, and it's a resistor and a capacitor in combination. Now, one thing about resistors and capacitors in a combination, they are called time circuits, because when you multiply, when you take and combine a farad with a ohm, when you work the units out, you get a second, okay? All right, that's really cool, isn't it? In other words, you get time. And you say, well, how does that work out? Well, folks, it does. Just take the units and start working it out, and you'll see that when you combine the units together, you'll notice that everything cancels out except for the what? Except for the second, okay? And so an RC circuit is actually a time circuit, okay? All right, now, of course, before it closes, of course, if it has a charge on it, you close this, then the voltage begins to move through the current circuit. And of course, it will move how fast or how slow based on how much resistance you have in the current. So immediately after it closes, the charge separation produces a potential difference, which causes a current, okay? And then, of course, the current begins to flow. All right, now, and how do we find that? Well, the initial current, here's how we find it, change in voltage initial over the total resistance that we have in the circuit. Now, at a time later, of course, eventually the current gets reduced down towards zero, and of course, once current's gone, then there's no more voltage. All right, now look, here's how we look at it graphically. Now, this is for a discharging capacitor, not a charging, but a discharging capacitor. Notice that as soon as the switch closes, notice what happens to currents. You have max current at I0, okay? And then it decreases down to real close to zero, okay? All right, same thing with voltage. Notice that you have maximum voltage, and notice how it decreases. So how do we express that mathematically? All right, the decay of voltage, this is for a discharging capacitor during and you need to write these down now. Make sure you write them down properly, because when we get to charging, the equations are a little bit different, okay? So notice for a discharging capacitor, notice the current is, the final current is equal to the initial current times e to the negative t over RC. Now, t over RC, that of course is your time constant, tau, and we'll get to that in a minute, okay? So notice, and yes, it is a negative exponent, okay? And of course, the charging of a capacitor, the voltage for discharging, is equal to the voltage across the capacitor initially times e to the negative t over RC, okay? And so there's your equation. So we can take the RC and combine them together and use a little Greek letter tau and say, and call this what we call a time constant, okay? So a time constant, in terms of time constant, the current and voltage will be what? This is how you would write it if you use the Greek letter tau, okay? All right, now what about for a charging capacitor? Oh, well, and by the way, if you have a time constant of 1, e to the negative 1 is 0.37, or 37%. So what does that mean? If we have a time constant of 1, in other words, after one time constant is what this is trying to tell us. If after one time constant, all right, then the voltage across the circuit is 37% of its initial value. Okay, so it has dropped down to 37% of its initial value. After two time constants, notice what it is. And you say, how do you get that? Okay, e to the negative 1 is 0.37 or 37%. E to the negative 2 is 0.13 or 13%. So after two time constants, you can see that the voltage is really getting down there now of its original voltage. Okay, all right, so if we have a large resistance that opposes flow of charge, so it increasing R increases the decay time, okay? Increases the decay time. A large capacitance stores more energy, so increasing C also increases decay time, okay? So if you go back and look at your equations, you can see that if you have a very high resistance, okay, then guess what? Then you're going to decrease the decay time, okay? All right, so what about charging a capacitor? Well, it's right the opposite of everything we just saw. The only thing that's not different, notice that the current is the same. Isn't that something? Isn't that something? Because regardless of whether you're discharging or charging, as soon as the switch is closed, you're going to have maximum current. Maximum current is going to exist whether you're charging it or discharging it, okay? If you're discharging the capacitor, that means it has maximum charge, maximum voltage. You're going to have maximum current. All right. If you're charging, well, as soon as you apply that voltage, guess what? Current goes up. Okay. All right. Now, but notice how the voltage changes. Now, notice here it's different. Now, why they put the E in here? That is the same as saying the initial voltage. Okay. In other words, your EMF voltage, your initial voltage. Notice it's 1 minus e to the negative t over RC, or we could say tau. And this is for a charging capacitor, okay? This is for when we charge a capacitor. And like I said, we will work some of these problems, and you'll see how these come into play, how it works, okay? All right, and that's it on lecture. Hope this helps.